This lecture is going to go over textures, and we're going to look at structures of sedimentary rocks. We can say that a little information provides clues to paleo environments. We'll start off with rounding. As an angular sedimentary particle is transported, generally in water, it collides with other objects as it travels. This process of abrasion is a mechanical process that leads to rounding off angular edges. Here we can see within a bed load, we get these series of movements that are going to eventually take an angular sediment and are going to round it. Thus, we can infer that a rounded inclusion, such as in a conglomerate, was transported some distance before forming the new rock, the conglomerate itself. That the inclusions are older than the conglomerate rock itself. We can look at sorting. Sorting is described as the uniformity of grain size. Sediment that is poorly sorted is said or considered to be, let's just say, heterogeneous mixture of different sizes of sediment. And here in this picture we see coarse, we see some medium sizes, and we see some fine grains. But sediment that is well sorted is homogeneous mixture of similar sized sediment. So here's another way we can look at sorting. We can take a look here at boulders. So we have this mountain, we have this kind of cartoon picture here, we have this stream, this river here. And we have the boulders, then we have cobble, we have gravel, into sands, and into silts and clays. The smaller particles take less kinetic energy to transport them. So we see this very graded sorting of soil. In this case, we're looking at the size of the sediment itself. We can apply that same concept of how looking at sediment that settles out of water in predictable ways. The size, density, and shape of materials influence the sequence in which particles settle. Placing a heterogeneous mixture of sediment into water, shaking it and watching it settle allows us to naturally simulate how settling occurs. So if I have this container, I've got the sediment in here, and I shake it up or agitate it, it's going to settle down from gravel to sand to silt to clay. And eventually the clay in suspension will slowly settle to the top. So in what order will these particles settle out? Well, based on what we know here, we'll just assume that they're all the same material. C is going to settle first, then A, then D, then B. The shape of the object matters too. It's all about surface area. So if I look at this graph here, fast and slow, we get different shapes that result. The rate or the velocity of the water current influences the net outcome of the particle shape. Fast-moving water tends to round particles, while slow-moving currents tend to just lead to more of an elongated shape, more of an oval. Still round, just not spherical, right? Not a sphere here. So even tiny variations in surface area affect the rate at which they settle, particularly if the sediment is the same in every other way. Surface area matters here. That flat, irregular particles have more surface area, so they settle slowly. Small rounded particles, less surface area, they settle more quickly. Crossbedding is a structural feature that here we can look at wind is traveling from the left to right. And we're going to get this characteristic pattern here. Observe the direction of water or wind flow. The gentle slope, right, we're going to start calling this the windward side, windward slope. And the steep slope here, what we'll call the leeward side, is a common appearance of deposition. Crossbedding is a result of deposition from the movement of wind or water. Crossbedding features show the direction of flow along with the energy in the transport. So if I use this kind of picture to make sense of, we could say here that the wind is going to be traveling, in this case, would be from left to right. The differences are going to be the amount of wind. So the angles in which the wind can travel or transport particles is going to vary in terms of the slope. Here we can see crossbedding from water, and here we can see a structure or landform from crossbedding from wind. So the windward and leeward sides of crossbedding. I want to make sure you make a drawing. And draw this picture right here and label this your windward, label this your leeward side. High velocity winds pick up sand grains on the windward side of the dune, right? It transports them upslope. On the leeward side of the dune, wind speed drops and sand grains are deposited. Grains accumulate in layers, forming crossbeds. So here's another picture that we can illustrate here. Wind travels in this direction, it's going to deposit sediment on the leeward side. It's going to be a steeper slope here, right? Because you have a directional flow of velocity or current here. That crossbed sets form as one ripple migrates over another. A single layer of crossbedding is called a set, and multiple layers are called cosets. So notice you can actually have differences in your crossbedding. Both the slope is going to tell you the wind speed, and the direction of them are going to tell you the direction of the wind. So in this picture here, you can actually see crossbedding. You can see that the wind direction also changed along with the speed. Sedimentary rocks often can get tilted and folded. Sedimentary rocks are laid down in horizontal layers called strata. Plate tectonic forces are always working, slowly putting tremendous force and pressure on the rock. Over time, it can break and tilt due to faulting. If the force and pressure is slow enough, the rock will actually bend, forming a fold. So a fault is going to be a direct break. It's going to be a change in it. A fold is going to be the bending of it due to what's just called differential stress from the sides. It's coming from the left and from the right. So over time, it's going to be able to fold. Sedimentary rocks that have been tilted are no longer situated the way they were laid down. Notice these are sedimentary rocks, but they're not parallel to what we would call the horizontal plane. They were moved by natural tectonic forces. They have been altered or modified from their original form. Here we can look at grain size. We can call it fine or coarse. Fine is just simply small, right? We can't see with the naked eye. That these are all fine-grained layers. We can actually see very definitive bedding planes here. And graded bedding is it changing from coarse to fine-grained due to deposition. So we get this sequence here. We get the coarse, we can call them pebbles, and then into cobble, into sand, and into silts and clays. And you just get a recurring pattern here. So these are graded bedding. Graded mean you go from bigger to smaller, coarser to finer. Whereas here we have bedding planes that are based on, these are all fine-grained sediment. Here we can look at ripple marks. If I look here, if I've got this current that's moving back and forth in, say, Lake Michigan or in an ocean, waveform ripple marks result in the to and fro motion of waves and have a symmetrical profile. Notice these are pretty symmetrical. But anytime we have current involved, current ripple marks form in response to water or wind currents flowing in one direction and have asymmetric profiles. We can apply that here when we look at our crossbeds. These are kind of superficial ripple marks. They just happen to be what we call, in this case, we're looking at crossbedding itself. And we'll end on mud cracks. Mud cracks form in very fine clay material that is dried out. As the moisture is removed, generally evaporation, the surface will split into cracks that extend down into the mud. These cracks form polygons on the surface of the mud. A polygon is a 5 or more sided feature with straight sides and defined angles. Where we find ancient mud cracks, we can infer that there was a marine environment that dried up. For example, a lake bed. We live in Lake County, Illinois. Mud cracks are actually very common.